with a problem like this, if this were a weak acid or a diprotic or a triprotic acid, you would not yet have the math skills to solve this problem. You only have the math skills at this point in time to solve this problem if this is a strong monoprotic acid. So the first question is this a strong monoprotic acid? So perchloric, if there's no hydro on the front of the name, then there's a polyatomic ion in the formula with oxygen in it. Perchloric then comes from perchlorate. And perchlorate is ClO4 with a 1 negative charge. The way you make that an acid is to put that together with as many hydrogen ions as are necessary to neutralize whatever the negative charge is on the ion, the anion. Okay, this is a negative ion, so we call it an anion. It's a polyatomic ion, so we call it a polyatomic anion. It has oxygen in it, so we call it an oxyanion. Okay? So we need only one hydrogen with a plus charge to neutralize that, and so we get a perchloric acid that is HClO4. This is perchloric acid. You know it is a strong monoprotic acid. It's monoprotic because there's only one hydrogen that can dissociate. You know it's a strong acid using the system that I've taught you, which is if the acid has 2 or more oxygens in the formula than hydrogens, it's strong. Okay, that's assuming it isn't an organic acid. All organic acids are weak. All right. So using that system, we know this is a strong and monoprotic acid. Therefore, it completely dissociates in water. Now, when you get to AP chemistry, you're going to have to be able to calculate pH and concentrations using acid ionization constants. And here's a table of acid ionization constants. And if you look at perchloric acid here on the top row, you can see that its Ka is large. It's so large, you don't need to know what the Ka is. You assume it's going to dissociate completely, so you don't worry about it. Now, that being the case, then what we need to find out is the molar concentration of the perchloric acid. Since we have 1.25 grams of perchloric acid, we've got to convert that into moles to get the molar concentration. You've got to have moles of solute over liters of solution. So let's calculate the molar mass of perchloric acid. We've got hydrogens and chlorines and oxygens. The atomic mass of hydrogen on the periodic table that you use in this class is 1.008. The atomic mass of chlorine we use on the periodic table we use in this class is 35.45. And the atomic mass of oxygen on the periodic table we use in this class is 16.00. Now we need to multiply all of these masses by the number of atoms in the formula. And so we get 64 as the total atomic mass of 4 oxygens. Now we're going to add all these together. Remember, there are empty slots over here on the right, or an empty slot with each number. So the digit that results from adding this to everything, this 8, is going to be underlined. It's going to be insignificant. So this is grams of perchloric acid. We're going to round it off to 100.46 grams of perchloric acid and show that equal to 1 mole of perchloric acid. Okay? All right. This is going to give us a conversion unit to convert this into moles. we're going to put grams on the bottom here so we can cancel the grams that are here. And then the other side of the equality statement goes on the top. Okay, so every time you have a conversion unit that is derived, it will be derived, it has been derived from some kind of equality statement. You might not know what that is, but you can figure it out from the conversion unit itself if it's written properly. All right, so now this allows us to cancel grams and the perchloric acid here. And since we want to find out moles per liter, we need the volume up here of the solution. Molarity is moles of solute over liters of solution. We've got it in milliliters, but converting to liters should be fairly easy. We want to put that on the bottom because we want our volume to be on the bottom. 22.25 milliliters of HClO4 solution. Okay, HClO4 solution is not the same thing as HClO4. This is the solute. This is both solute and solvent together. We want to put that over 1, but we need to convert the milliliters into liters. So you need to remember and write down for yourself that 1,000 milliliters equals 1 liter. Okay, that'll allow us to build a conversion unit to do that. So I'm going to put 1,000 milliliters on the top so that it'll cancel out milliliters on the bottom here. And I'm going to put 1 liter on the bottom. Okay, that then allows us to cancel out milliliters, 1 on the top, 1 on the bottom. And when we're done, we have moles of solute, the perchloric acid, over liters of the perchloric acid solution. That's the molar concentration. So we're going to take the 1.25, and multiply it by 1,000. Hit enter, and then divide separately anything on the bottom. We've got 100.46 on the bottom. We're going to enter there. We've also got 22.25 on the bottom. So we're going to divide by 22.25 on the bottom. And we get this number here. We want 3 significant digits. To figure out the number of significant digits you need when you're doing multiplication and division is you want to look at the problem and find all the measured and calculated numbers in the problem. Choose the measured or calculated number with the least digits and write your final answer with that same number. Well, this number here of the measured and calculated numbers has the least digits. This is a measured number, calculated number, calculated number. These are absolute values here, so we don't even use those. We ignore anything like milliliters and liters and things like that. So 3 digits is how many digits we want in our final answer. 0, this leading 0 here is not significant. Okay, this is our first significant digit, 1, 2, 3. Underline from there over. Should have written it there. These are this is in moles of HClO4 over liters of HClO4 solution, and then round off. So 0.559, and moles of this solution over liters of that same solution is molar concentration. That's the way you symbolize it. Okay? Now, since this is a strong acids completely dissociate, which is the reverse of this. Okay, complete dissociation using the Arrhenius theory says that all of the hydrogens completely dissociate. Okay, so if I have 1 mole of this, then I must have 1 mole of this when I'm done, because it completely dissociates. And so if I have a mole up here on the top of this, that's the same thing as a mole of this. And so if this is the molar concentration of a strong monoprotic acid, and this only works if it's a strong monoprotic acid. If this is the molar concentration of this acid, then the molar concentration of HClO4 is also the molar concentration of hydrogen ions. Okay? And using the Bronsted-Lowry theory, we would take the hydrogen and join it up with a water molecule. and we'd have a chlorate ion left over. Okay, and so for every one of these, I get one of those. So if I have 1 mole of this, I got 1 mole of that, and therefore the molar concentration of this is also the molar concentration of the hydronium ion. So 2 answers we have already. We have this one and this one already because, and only because, this stuff is strong and monoprotic. Okay? What? Yeah?
But the only problems we have would be like that, right?
Yeah, you don't have the math to do anything else at this point in time. Okay, now, that gives us 2 of the answers the question asks for. Okay? These 2 right here. Now we got to find these 3 right here. All right? So to find the pH, we take the negative log of the hydrogen ion concentration or the negative log of the hydronium ion concentration, and that's the same thing. This is just the way we calculate it and understand it using the Arrhenius theory of acids. This is the way we calculate it and understand it using the Bronsted-Lowry theory of acids. But the value of this molar concentration is the same number of moles per liter. And so we're going to plug in negative log of 0.559. Okay? So, negative logarithm, and we're using base 10, but on this particular calculator, if you skip over that, it's going to assume base 10. So all I got to do is put in 0.559. Okay, and see it puts in the base 10 here already. And so that's our pH, 0.25288. pH is a unitless answer, but we need to round it off. Now, technically, we should be rounding off to 4 digits, but that's a rule we don't learn about at this level anyway, so we're going to assume there are 3 digits here because we have 3 digits here. We're going to use the same rule for rounding off in this class as we use for multiplication and division. So we're going to assume 3 significant digits then, and we're going to say our pH is 0.253. Okay? Now, calculating the pOH, really I can do all of these things in 2 different ways. Okay? What I did was to find the hydrogen ion or hydronium ion concentration in the upper left here, and then found the pH. I can find the pOH using this equation right here, 14 equals pH plus pOH. Or I could have started with this and went to the hydroxide ion concentration using this equation, Kw equals hydrogen ion times hydroxide ion concentrations. And then go this way. I can go around either way, left or right, or clockwise and counterclockwise. Doesn't really matter. Okay? Since I have the pH like this, I'm going to go ahead and use this equation to find the pOH. That 14, and you can put as many zeros as you want to after that. 14 equals pH plus pOH. And just to be clear, this only works at about room temperature. Okay? You get off of room temperature, pHs kind of change a little bit. All right? The lower the temperature, the lower the pH, the higher the temperature, the higher the pH, without really changing the effect at all. All right. So then if I plug in this number, what we get is that pOH is going to be equal to 14.000 minus 0.253. And we get 13.747. Okay, that's the pOH. All right, going back to our chart again, we now have pOH, and we also have the hydrogen ion or hydronium ion concentration. We can get to the hydroxide ion concentration from here to here, or from here to here. Either way works. Does that make sense? All right, I want to go from here in the upper left-hand corner to here in the upper right-hand corner. Not that it matters a great deal. Okay, so I want to use Kw equals the hydronium ion concentration times the hydroxide ion concentration. We calculated the hydronium ion concentration to be 0.559 molar. We just need to know what kW is. Let's look at the test references, because these test references list this a little bit differently, and I want to make sure we're as clear as we can be. Okay, here it is. This test reference says kW is equal to the hydroxide ion concentration times the hydrogen ion concentration is equal to 1.0 times 10 to the negative 14. You need to know that hydrogen ion concentration is the same thing as hydronium ion concentration. So since I'm using hydronium ion concentration, okay, that's going to be the same thing as what's in this equation right here. Now, 1.0 times 10 to the negative 14. You can put more zeros on there. It can be 1.00 or 1.000. Okay? So, huh?
Why would you want to put more zeros on it?
How many digits do I have after the decimal place here? Yeah, I got 3 after the decimal. But if I want to keep up with all the digits and not have it round off, to smaller numbers, or I'm trying to avoid propagating an error too much. Okay? All right, so by rearranging this, I get kW over the hydronium ion concentration equals the hydroxide ion concentration. Does that make sense? You understand what I just did in my head? Do I need to show you on paper? Okay. So kW, we said, is 1.000. I'm just going to put 3 zeros on here, times 10 to the negative 14. Now, the test references don't say what the units of measurement are. I want you to know this is molar squared. All right? The values in your test references, you have to know a little more than that. Okay? And the hydronium ion concentration is 0.559 molar. Okay? Now let's look at units here, because we want to cancel units using dimensional analysis. Molar squared is the same thing as molar times molar. Okay, so molar times molar is equal to molar squared. Would you agree with that? Anybody have a problem with that? That's what squaring something means. Okay?
But what's the purpose of it?
I'm going to show you. Can you give me just a minute?
Uh-huh.
I'm finishing a problem here, okay? All right. That being the case, then, I can cancel out 1 molar up here with that one on the bottom. Do you understand what I'm talking about? All right. And now all we have to do is plug in the calculator, these values, to get an answer. Okay? So 1.000. Here's my exponent button down here in lower left. We want to change the sign for negative 14. I'm going to put all this in parentheses. I'm going to divide by, and then I'm going to put 0.559 on the bottom. And so we get a hydronium ion concentration of 1.78891 times 10 to the negative 14. Again, you need to remember this e to the negative 14 on your calculator means times 10 to the negative 14. Okay, and because we have molar left, that's a unit we're going to keep. I'm going to round it off to 3 digits because I have 3 digits here. 1, 2, 3, underline, use an arrow to show that we're rounding off. That's the only operator that's allowed to show rounding off. 1.7, the 8 makes the 8. This 8 makes this 8 round up to a 9 times 10 to the negative 14 molar. And that's the last of those 4 answers.